Hi everyone. So in this video, I'm going to go over about 30 problems related to the practice final exam. Below, as usual, you can find a copy of the questions, a copy of the answers, as well as the times, and you can watch any individual question that you want. So the first thing is, it is important to study the practice midterm as well because the final exam is cumulative, and this is absolutely true. There's a video for the practice midterm as well, and again, you can find copies of the practice midterm and the answers on that video. Question 2 says, when 0.0862 grams of zinc is reacted with excess HCl, 32.27 milliliters of hydrogen gas is collected. If the pressure of the hydrogen gas is 0.976 atmospheres at 293 K, what is the experimental molar mass of zinc? And then it gives us the zinc 2 plus. So this was from the first part of the class, but there is a few questions here just to review those things because this is the final review. So let's go ahead and do this. So first things first is we need a reaction between zinc and HCl. So we have zinc as a solid plus HCl, which is hydrochloric acid dissolved in water, so that is aqueous. When we do this reaction, we get zinc 2 plus, which means we get one zinc and two chlorides, ZnCl2, and that's soluble, so it's aqueous. And we also get hydrogen gas. Now we have two Cl's and two H's, so we need two HCl's. So in this case, we use excess HCl, so we're not worried about the limiting reagent. We know the limiting reagent is zinc, and you actually used magnesium when you did this, but here we're doing it with zinc, just so it's a little bit different. So what we need to do is we need to calculate the molar mass. Now this is somewhat unfamiliar to you, because usually if you wanted to find a molar mass, you would simply look on a periodic table and find a molar mass. Note that you don't want to do that here. Here you want the experimental molar mass. Well, experimentally, the molar mass of, in this case, zinc is equal to the grams of zinc divided by the moles of zinc. In this case, we're given the grams of zinc right in the problem. The moles of zinc, though, we need to find. Fortunately, we have the volume of hydrogen. Hydrogen's a gas, so we can use the ideal gas law. The ideal gas law being PV equals nRT, where P is the pressure in atmospheres, V is the volume in liters, N is the moles, R is 0.08206, that's liter atmospheres per mole K, and T is the temperature in Kelvin. So in this case, we want to solve for N, so divide both sides by RT. N equals PV over RT. Well, in this case, the pressure of the hydrogen is 0.976 atmospheres. The volume of the hydrogen is this, but we have to convert this to liters, 0.03227 liters divided by 1,000, so 0.032, I'm going to try to write it up here, 0.03227 liters divided by, R is a constant, 0.08206, that's liter atmospheres per mole K, times the temperature in Kelvin, and the temperature in Kelvin is given 293 K. When we do that, we find that the moles of the hydrogen is 1.3099 times 10 to the minus 3 moles of hydrogen. Now, we need to figure out how many moles of zinc we have. If you look here, one zinc gives us one hydrogen. So if you instantly realize this is the moles of zinc as well, good. If not, you could take the 1.3099 times 10 to the minus 3 moles of hydrogen times, for every 1 mole of hydrogen from the balanced chemical equation, we reacted 1 mole of zinc, which of course then gives us 1.3099 times 10 to the minus 3 moles of zinc. So either way you do it, these number of moles are the same. Well, now we have the two parts of our equation over here. We have grams and we have moles, so we can plug in. So 0.0862 grams of zinc divided by 1.3099 times 10 to the minus 3 moles of zinc. And when you do that math, you get 65.8 grams per mole for the molar mass of zinc, which is choice letter B. Question number 3 says, according to the ideal gas law, what is the volume of gas at absolute zero? Well, at absolute zero, the volume of a gas is zero. You may recall that in the ideal gas law, we do not consider the volume of the gas molecules themselves, the actual molecules of the gas. We only consider the space between them. Well, at absolute zero, there is no space between them, so the volume of any gas at absolute zero is zero. Number 4 says, theoretically, which of the following has the lowest freezing point? So this is a freezing point depression question. So delta TF equals I, the Van Hoff factor, KF, the freezing point depression constant, M, times the molality. Well, if you notice here, we have 1.5 molal sugar. We have 1 molal NaCl, and we have 1 molal CaCl2, and we have pure water. Well, anything dissolved in the water is going to give it, apparently I have an update here, is going to give it a lower freezing point. So pure water is not the answer. So let's look at sugar. Here, I equals 1 because sugar is a covalent compound. C12H22O11 is sucrose table sugar, and it's covalent, so it doesn't break up into ions. In the case of NaCl, if we have NaCl solid, it breaks up into Na plus aqueous plus Cl minus aqueous. So freezing point depression is a colligative property, which means it's dependent on the amount of particles, but not the identity. So this breaks up into 2 particles, so I equals 2. In the case of CaCl2, we have CaCl2 solid, which breaks up into Ca2 plus aqueous and 2 Cl minus aqueous, because there's 2 Cl's, so here I equals 3. So what basically happens is we have essentially double the concentration of NaCl, because it breaks up into 2 things, and triple the concentration of CaCl2, because it breaks up into 3 things. Well, double the concentration of NaCl is more than this one, and triple the concentration of this is more than both of these. So this is going to have the lowest freezing point. You could, if you wanted, calculate delta TF in each case. But in this case, I is going to be the overriding factor because the concentrations are relatively close together. Number 5 says, what is the theoretical Van Hoff factor for CuCl2? Well, if we take CuCl2 solid, remember all ionic compounds are neutral, so this has 2 negative chlorides, so copper must be 2 plus. We get Cu2 plus aqueous plus 2 Cl minus aqueous, which means we have a total of 1, 2, 3 things in solution. So here I equals 3. So therefore this is the theoretical Van Hoff factor, because when we dissolve this, it breaks up into 3 ions in solution. You'll note that this is very similar to the final project that we did this year, where we used copper acetate and nickel acetate and cobalt acetate, but they were all still I equals 3 as the theoretical Van Hoff factor. Question 6 says, when 40 grams of NaOH is added to make 550 grams of solution, the temperature increases from 22 degrees C to 41.3 degrees C. What is the heat of solution per mole for sodium hydroxide per mole? And then it gives us the specific heat capacity of the solution. Well, the first thing I want to do is I want to convert these grams to moles. You don't have to do this first, but if we have, if we have 40.0 grams of NaOH times 1 mole of NaOH, per, the molar mass happens to be 40.00 grams of NaOH, means we have 1 mole of NaOH in solution. Sorry, that's a little off the screen. So we have 40 grams divided by the molar mass, which happens to be 40 Na plus O plus H, and we have 1 mole of NaOH. This makes our life easier. It means we don't need to calculate per mole. We dissolved exactly 1 mole. So whatever we get for the heat of solution here is in kilojoules per mole, because we did exactly 1 mole. So we need the equation, delta H of the solution equals negative M, where M is the mass, times C sub S, the specific heat capacity, which is given, times delta T. which we need to figure out in a second here. So to figure out delta T, we need delta T equals TF minus TI. Well, the final temperature is 41.3 degrees C minus the initial temperature, which is 22.0 degrees C, which gives us an overall temperature change of 19.3 degrees C. We can now plug in these values. So the mass of the solution is 550 grams. The specific heat of the solution is 4.18 joules per gram degrees C. And the change in temperature is 19.3 degrees C. When we do that, we get, this is negative, sorry, the delta H of the solution is equal to negative 44,400 joules. The answers are all in kilojoules per mole. Remember, we already talked about we used exactly 1 mole, so we just need to convert this to kilojoules divided by 1,000, which is 44.4 kilojoules per mole. Note that if we hadn't have used exactly 1 mole, we would have needed to divide by moles. In fact, we did divide by moles. We just divided by 1, so we got the same number. This is negative. I keep forgetting the negative sign. Another thing to remember, this is clearly going to be an exothermic process, or have a negative heat of solution, because when we dissolved the NaOH in water, the temperature increased. So heat energy was released as the temperature increased. So here we get negative 44.4 kilojoules per mole. So number 7 says, how many single bonds and how many double bonds are present in the best Lewis structure of SO3? I'm not going to spend a lot of time going over Lewis structures. There's a couple of them on this problem set. If you'd like a more thorough review of Lewis structures, just go to our YouTube channel and you can find a long video. Well, it's actually like 5 videos, and it's about an hour long, where we thoroughly cover Lewis structures. But here, I'm going to just go through it relatively quickly. So we have SO3. So first thing we do is we count the valence electrons. So we have 6 plus 3 times 6, which is a total of 24 electrons. We put the least electronegative atom in the middle, sulfur, and we bond it to 3 oxygens. I've now used 2, 4, 6 electrons. I'm going to now start filling octets. 8, 10, 12, 14, 16, 18, 20, 22, 24. I have now used 24 electrons. Now I want to see if I've filled the octets. And what I have not done is filled sulfur's octet. So I need to make a double bond because I have no more electrons and I want to fill sulfur's octet. So I'm going to go ahead and make a double bond here. And what I end up with is S bond O, like this, bond O. These two just went along for the ride. Double bond O, like this. Now I need to calculate the formal charges. So we want to compare the number of electrons these want to have around them to how many they actually do. Remember to count the dots as 1 and count the dashes as 1. There's 2 electrons in this bond, but formally 1 belongs to sulfur and 1 belongs to oxygen. So oxygen wants 6 electrons around it. It's in 6A of the periodic table. Let's see how many it has. 1, 2, 3, 4, 5, 6. It's neutral. How about this oxygen? It wants 6 and it has 1, 2, 3, 4, 5, 6, 7. It's negative. This is the same. It has 7, so it's negative. How about sulfur? Sulfur wants 6. It's also in 6A, just below oxygen. And it has 1, 2, 3, 4. It's missing 2 electrons, so it's plus 2. This, although the octets are full, is not ideal as far as the Lewis structure goes because you have high formal charges. So remember that we want to minimize those formal charges. Well, the way we could do that is take some electrons away from oxygen, make a double bond, and make a double bond. But before we do that, we need to ask ourselves, can sulfur expand its octet? Sulfur is in period 3 of the periodic table, and period 3 or lower on the periodic table elements can expand their octets. So I'm going to go ahead and make 2 more double bonds, like this. And now I have effectively taken an electron away from this oxygen, making it neutral, taken an electron away from this oxygen, which makes it neutral, and added 2 electrons onto sulfur, which makes it neutral. This is the best Lewis structure. Now I can answer the question, well, what is present? 1, 2, 3 double bonds, which is choice letter D. Number 8 says, what is the molality of a NaCl solution if 0.822 grams of NaCl is dissolved in 485 grams of water? So molality, which is a temperature-independent unit of concentration, M is equal to moles of solute divided by kilograms of solvent. So we use this when we're doing temperature studies because molarity changes. It has volume in the bottom, and volume changes as temperature changes. So it's not a good unit of concentration for studying temperature changes. So I'm going to do this as dimensional analysis. You don't have to, but that's how I'm going to do it. So I'm going to go from grams of NaCl to moles of NaCl. And then I'm going to divide that by, this is not dimensional analysis, kilograms of water, because moles divided by kilograms gives me the molality. So that's my goal. So I'm going to start with the grams given, 0.822 grams of NaCl, which is given. I'm going to convert that to moles using the molar mass, which is 58.44 grams of NaCl, just Na plus Cl on the periodic table, and 1 mole of NaCl on the top, times, now I want to divide by the volume of water in kilograms, mass of water in kilograms, which I want to take this and divide by 1,000, so I get 0.485 kilograms. But I want to divide, so I put a unitless 1 on the top, which means divide, and then on the bottom I put 0.485 kilograms. And when I do that math, I get 0.0290 molal, or because the answers are in scientific notation, 2.90 times 10 to the minus 2 molal. And this is choice letter E for number 8. Question 9 says, consider the reaction and information in Excel below. What should be entered into D3 here in order to calculate Kc? Well, Kc for this equilibrium reaction, and any others really, is products over reactants. So we want the concentration of FeSCN 2 plus over the product over the two reactants. Concentration of Fe3 plus, concentration of SCN minus. So this is the formula that we want to enter in here, but we're given it in Excel. The first thing we need to note is that we want to put in the equal sign. That concentration of FeSCN2 plus at equilibrium is in cell C. So C3. So we want to put C3 divided by, so a slash. Now what do we need to multiply? This times this. However, because of order of operations, we have to put in parentheses the A3, the concentration of Fe3 plus at equilibrium, times, which is a star in Excel, the concentration of B3, or the concentration of SCN minus. So we want these in parentheses, otherwise we'll take this, divide by this, and then we'll multiply by this. But what we really want is, we want this divided by this times this, so these must be in parentheses because of order of operations. So this is what we should enter into this Excel file, which is choice letter A here. Number 10 says, given the fictitious reaction below, calculate the value of Kc for the reaction if the equilibrium concentration of X is this, Y is this, and Y2 is this. So the first thing we want to do is we want to write the equilibrium constant expression, Kc, and its products over reactants. So Kc is the product, concentration of X, Y2, over the reactants. There's only one X, so concentration of X, and then there's two Y, so concentration of Y has to be squared. So it's products over reactants. Now we can plug in the values. The concentration of XY2 is given 0.216. The concentration of X is given 0.214. And we want to multiply that by the concentration of Y squared, or 0.114 squared. When you do this math, you find that the equilibrium constant for this reaction is 77.7, which is choice letter C. Number 11 says, give the characteristic of a second order reaction having only one reactant, and it asks us about the rate. So for a second order reaction with reactant X, the rate equals K times the concentration of X squared. So the rate is proportional to the square of the concentration of the reactant X. And if we read through the answers, the only one that says that is choice letter E. So for a second order reaction with only one reactant, this is the rate law. Number 12 says, what is the Ka of formic acid, a monoprotic weak acid, if a 0.05 molar solution has a pH of 2.5727? Well, let's start with the reaction. So we have H4 formic acid, which is aqueous, reacting with H2O, which is a liquid, and it's in equilibrium with H goes with this, so we get H3O plus, aqueous, and FOR minus, aqueous. So this is the equilibrium reaction. The Ka for this expression, Ka, products over reactants. So it's concentration of H3O plus, concentration of FOR minus, over concentration of HFOR. Now, how are we going to find these things? Well, the first thing to realize is that these two concentrations have to be the same. Because for every one of these that reacts up with water, we get one of these and one of these. So the concentration of H3O plus equals the concentration of FOR minus. But then we're given the pH, which will allow us to find the concentration of H3O plus. So the concentration of H3O plus equals 10 to the negative pH, or the concentration of H3O plus equals 10 to the negative 2.527, or the concentration of H3O plus equals 2.972 times 10 to the minus 3 molar in the calculator. So now we know the concentration of H3O plus, but we realize the H3O plus and the FOR minus are the same. Now, technically speaking, we could subtract this concentration from this concentration, but because this is just a small percentage of this one, we don't actually need to do that. Specifically, it's less than 10% of this. Now, if you want to subtract it, you're going to still get a very similar answer, and you can do that, and it wouldn't be wrong. But in this case, I'm not going to bother. I'm just going to put in these two values and then put in this one, and it avoids us having to make an ice table, and it avoids using the quadratic equation if we don't know this concentration. There's none like that on this set, though. All right, so now we can plug in. So the concentration of H3O plus we just found, so 2.972 times 10 to the minus 3, which is also the concentration of FOR minus, so 2.972 times 10 to the minus 3. And then the concentration of HFOR is given, which is 0.0500. When we do this math, we find the Ka is 1.77 times 10 to the minus 4, which is choice letter B for number 12. If a monoprotic weak acid has a Ka of 6.35 times 10 to the minus 6, what concentration of acid is required to make a solution with a weak acid solution with a pH of 3? All right, there's some typo here. So basically we have a Ka of a weak acid solution, and we want to make a weak acid solution with a pH of 3. So let's go ahead and look at how we're going to do this. If you haven't watched question 12, I recommend you start by watching question 12. So in this case, we have HA, aqueous, reacting with water, which is a liquid, and it's in equilibrium with H3O plus, aqueous, and A minus, aqueous. And the Ka of this equals the concentration of H3O plus times the concentration of A minus over the concentration of HA, just like in the previous question. In this case, we're given the Ka, and we can find the H3O plus, and HA is the variable. In the previous question, the Ka was the variable. So how are we going to find H3O plus and A minus? Well, just like before, we need to realize that the concentration of H3O plus equals the concentration of A minus. Why are they the same? They're the same because every time HA reacts with H2O, we get an H3O plus and an A minus. So we get one of these and one of these. They have to be the same. Well, how are we going to find the H3O plus? Well, the concentration of H3O plus equals 10 to the negative pH. In this case, the pH is a whole number. So the concentration of H3O plus equals 1.00 times 10 to the minus 3, because it's just 10 to the minus 3, but since it's 3.00, I guess technically it's 1.0 times 10 to the minus 3, because this is 2 sig figs. Anyway, we have 1.00 times 10 to the minus 3 for the concentration of this, which is also the concentration of A minus. Well, now we can plug in. We have Ka, which is 6.35 times 10 to the minus 6, which equals this one squared, 1.00 times 10 to the minus 3, times 1.00 times 10 to the minus 3, divided by the concentration of HA. So I plugged in the two I knew, which again are equal. I don't know HA, and I plugged in the Ka, which I'm given in the problem. Now, cross multiply and then multiply these together, and what I get is 6.35 times 10 to the minus 6 times the concentration of HA equals these two multiplied together, which is 1 times 10 to the minus 6. Now divide both sides by 6.35 times 10 to the minus 6, and I get concentration of HA, because it cancels out over here, equals 0.157 molar. Again, we're not subtracting out this concentration. We're assuming that it's less than about 10%, so we don't subtract it out. And this is our answer here, which is choice letter B for number 13. Question 14, it says, which of the following deviations from the known melting point are generally present for an impure compound? So this is one you just need to know. You do get a cheat sheet, so you could use your cheat sheet to do that. But you're going to get a lowering of the melting point range and a broadening of the melting point. These are the two deviations. And this is answer D, because both of those are 2. You do not get a sharpening of the melting point range. That one is not true. Again, you get a cheat sheet, so you can just put that on there. Number 15, it says, consider the following reaction at equilibrium. It says, what effect will adding CO2 have on the system? So this is a Le Chatelier's principle question. So if we add CO2, the reaction is going to shift to remove CO2. So Le Chatelier's principle, put generally, is reactions shift to remove disturbances in the equilibrium. So if we add CO2, the reaction is going to shift to the right to get rid of CO2. And letter B says the reaction will shift to the right in the direction of the products, which is what's going to happen if we add more CO2. Notice that if we decrease CO2, the reaction would shift left, right in the exact same way. So if we decrease this, we'd get more CO because the reaction would shift to just remove the disturbance in the equilibrium. If we decrease the amount of CO2, then it would shift in the opposite direction. Again, this is Le Chatelier's principle. Number 16 says, which calculation allows us to determine the precision of a measurement? So, percent error is the accuracy. This is comparing a value to a known or accepted value. RSD, or relative standard deviation, is comparing each value to each other. This is a measure of precision. R squared is a measure of how well the data fits the curve. So basically, if all your points fall on the curve of a line, your R squared will be close to 1. And the temperature has nothing to do with anything. So again, this tells you about accuracy, this tells you about precision, and this tells you how well your data fits the curve. Number 17 says, what is the limiting reagent in the following reaction if 4 grams of methane is reacted with 7.1 grams of oxygen? And then we're given a reaction. So in this case, it doesn't ask us specifically about which product we form. So I'm going to use water, but you could use CO2. Just be consistent. So for methane, I'm going to go from grams of CH4 to moles of CH4 to moles of water to grams of water. Again, if you wanted to go to CO2, that's fine. Just make sure you convert O2 to CO2 as well. For oxygen, I'm going to go from grams of O2 to moles of O2 to moles of water, because I already chose water, to grams of water. So this is basically what I'm going to do. I'm going to see which one gives me less water, and then therefore that's going to be the limiting reagent. So let's see what we have. So if I start with 4 grams of CH4 times 1 mole of CH4 has a molar mass of 16.05 grams of CH4. Now I need to convert it to water using the balanced chemical equation. So for every 1 mole of CH4, because there's 1 in the balanced chemical equation, I get 2 moles of H2O, again from the balanced chemical equation. The reason I chose water is because I know the molar mass of water off the top of my head, so now I'm going for moles to grams. So for every 1 mole of water, it's 18.02 grams of water. And when I do all that math, I get 4.5 grams of water. Now, I don't know if that's the limiting reagent yet. I just know that if I react all my methane, I get 4.5 grams of water. I need to repeat this entire process for oxygen and see how much water I get. So in this case, I want to take 7.1 grams of oxygen, and I want to convert it to moles. So for every 1 mole of oxygen, it's O2, so it's 32.00 grams of oxygen. Now I want to convert it to moles of water. Well, in this case, 2 moles of oxygen gives me 2 moles of water. And then finally, for every 1 mole of water, I get 18.02 grams of water. And when I do that, I get 4.0 grams of water. So using all of my oxygen gives me less water. That means that oxygen is my limiting reagent, and in this case it doesn't ask for it, but my theoretical yield of water is 4 grams. So here the answer is choice letter D. Number 18 says, a student is trying to determine the volume of a flask and compare it to the known volume. After performing her measurement 10 times, she calculates her RSD to be 352 ppt and her percent error to be 46%. Which of the following statements about her results are correct? Well, if the RSD is 352 out of 1,000, her data is not very precise. If her percent error is 46%, her data is not very accurate. So remember, percent error tells us about percent error tells us about the accuracy, and RSD tells us about the precision. But in this case, the values are neither accurate nor precise. Number 19 asks us, what is the formal charge on the starred atom below? Lone pairs, if present, are shown in the structures. So here we have no lone pairs. So if we look at this starred atom, we're looking at this nitrogen here. Nitrogen wants to have 5 electrons around it. Remember, count the bonds as 1 because for every bond, 1 belongs to nitrogen and 1 belongs to carbon. So it has 1, 2, 3, 4. Nitrogen has 4 electrons around it, but it's in 5a, so it wants 5 electrons around it. Said another way, it's missing an electron. Something that's missing an electron has a +1 charge. Number 20 says, which of the following statements is true about liquid-liquid extraction? So, the general rule is like dissolves like. And solubility is not exactly what we're talking about here. We're actually talking about affinity, which is not exactly the same thing. But for the sake of simplicity, as you're just starting to learn about this stuff, I'm going to use this as an example. So what's a like in like dissolves like is essentially intermolecular forces. So polar and ionic solutes dissolve in polar solvents. That's what's like. Polar solutes, the thing that dissolves in polar solvents like water. Non-polar solutes dissolve in non-polar solvents like hexane. And we did this with lauric acid, I think it's coconut oil, dissolving in hexane in the first semester. And we did this again in the organic acid-base extraction type stuff. So here we have non-polar solutes have a strong affinity for non-polar solvents. This is why if you take a bodily fluid that has a drug of abuse in it and you extract it with an organic solvent, oftentimes the drug will go into the organic solvent because the drugs tend to be organic, relatively non-polar molecules, generally speaking, and they'll go into the organic solvent. And this is how they used to. They use a slightly different method now at the State Police Crime Lab. But this is how they would extract the drug of interest from all the other stuff that they don't want to shoot into their instruments. So question 21 builds off of question 20. It says the molecule below would be found in which layer? Well, this is an organic molecule, so you would think it's relatively nonpolar, but then you see this minus and plus. This makes it ionic. Ionic compounds dissolve in polar solvents. The polar solvent here is the aqueous solvent. Aqueous means dissolved in water. So because this is ionic, you would find it dissolved in water. Number 22 says, which of the following is a way you could tell a reaction taking place in a test tube is endothermic? So endothermic means requires heat energy to happen. So if this requires heat energy and you're the surroundings, right, this would be the test tube, the reaction in the test tube would be the system, then if it's endothermic, it's because it's taking heat energy away from you, if you're the observer. So you can look at this or touch the tube and feel how it feels. So the test tube would become cold to the touch because it's taking energy away from the surroundings, including your hand if you're touching it. Therefore, this is endothermic. If a reaction is exothermic, then it releases heat energy, and therefore it would feel hot to the touch. But in this case, for 22, it's choice letter A because it's endothermic. Number 23 says, what is the purpose of a buffer solution? Well, generally speaking, a buffer solution is to resist changes in pH. In a little bit more detail, buffer solutions generally contain a weak acid and its conjugate base. So the weak acid would react with any added base to resist changes in pH, and the conjugate base would react with any added acid to resist changes in pH. So whether an acid or a base is added, a buffer's job is to resist changes in pH, and we just discussed how it does that. Number 24 says, what are the four variables in the Beer-Lambert law? So A equals E, B, C, where A is the absorbance in absorbance units, E is the molar absorptivity coefficient, which is essentially a measure of how strongly a molecule absorbs light, B is the path length, and C is the concentration. So the answer here is letter B. The take-home message here is the absorbance and the concentration are directly proportional over the linear range, which you did in both the final project this year, and you did this in the introduction to absorbance experiment. Number 25 says, what is the pH of a buffer? When is the pH of a buffer equal to the pKa of the acid used to make it? Well, we can look at the Henderson-Hasselbalch here. pH equals pKa plus log of A minus over HA. So when are these two things equal? And you did this in lab. This was the second method of determining the pKa of a buffer. It was by making these two things equal. When concentration of A minus equals the concentration of HA, the ratio is 1, because you have the same number divided by itself. So this becomes 1. The log of 1 is 0. So if this becomes 0, then pH equals pKa. So it's when the concentration of the acid and the base are equal, which is choice letter D here. Number 26 says, what is the charge on the central atom of carbon dioxide? So we got to draw the Lewis structure. Count the valence electrons. 4 plus 2 times 6, which is 16 electrons. Carbon goes in the middle. We bond it to 2 oxygens. So we've used 2, 4, 6, 8, 10, 12, 14, 16. You'll notice carbon doesn't have an octet. Making one double bond isn't enough. So I want to make 2 double bonds. And what I get is C double bond O, like so. And this is the best Lewis structure. carbon wants to have 4 electrons around it. It has 1, 2, 3, 4. Remember, count the dots as 1, counts the dashes as 1. If something has the proper number of electrons around it, because carbon has 4 valence electrons and it has 1, 2, 3, 4 electrons around it, it is neutral. So here, the formal charge on carbon is 0. Again, as I said in a previous example where I went over Lewis structures, on YouTube you can find a quite extensive, I think it's a 5 or 6 part series, it's about an hour total in length, that goes over in detail how to do Lewis structures. I'm not going to spend a lot of time here, but if you'd like to review that, please feel free to do so. Number 27 says, what type of molecules are soluble in hexane and why? So here we want to use like dissolves like again. And if you haven't viewed question 20, it would be a good idea to take a look at that, where like dissolves like is discussed in more detail. But basically, polar and ionic molecules are soluble in polar solvents like water. Non-polar solutes are soluble in non-polar solvents like hexane. Hexane is C6H14. It only contains carbon and hydrogen, so it's non-polar. So non-polar molecules, because hexane is also non-polar. So that is the best answer to question number 27. Number 28 says, which of the following is true about a solution of yellow dye? So, over a range of 0.1 to 1 absorbance units, the concentration in the absorbance are directly proportional. So, they are proportional to the concentration. The other thing to remember is that if you have a yellow dye, it doesn't absorb yellow light. Okay, they absorb their complementary color. So a yellow dye should absorb blue light. So the molecules in solution absorb blue light proportionally to their concentration. So this is what's important. As you change the concentration, the absorbance goes up. And also, yellow dye doesn't absorb yellow light, yellow dye absorbs blue light. To briefly explain this, remember that what's hitting us all, whether it's from the sun or from the light bulbs, is white light. White light is all the colors of light. So, if all the colors of light hit a solution and the blue light is absorbed, what we see is yellow. If the yellow light was absorbed, we would actually see something that looks blue. So that is basically how it works. Number 29 says, which of the following is the expression used to solve for the equilibrium constant of this reaction? And we have hydrogen gas plus oxygen gas yields water liquid. Now this isn't a particularly reversible reaction, but what's important here is liquids don't go in the equilibrium constant expression. So Kc equals 1, because there is really no product here because this is a liquid. Concentration of H2 squared concentration of O2, like so. So this case, these are your reactants, and we put a unitless 1 on top because there is no product that's involved in the equilibrium constant expression, again because this is a liquid. Solids and liquids are not involved, gases and aqueous compounds are. So this is, to answer this question, is choice letter C. Number 30 says, what is the Van Hoff factor of a solute that lowers the freezing point of water by 3.98 degrees C when at a concentration of 2.14 molal? And it says the freezing point constant for water is 1.86 degrees C per molal. So we need to use the freezing point depression expression here. Delta T F equals I, the Van Hoff factor, Kf, the freezing point depression constant, times m, the molality. Well, in this case, we're given all the variables except I. So delta TF is 3.98 degrees C. I is the Van Hoff factor, that's what we're trying to find. The Kf is 1.86 degrees C per molal. And the molality is 2.14 molal. When we multiply these two together, they come out to be 3.98. Then we divide both sides by 3.98, and we find that I equals 1 in this case, so which is choice letter D. So here we have a covalent compound dissolved in water, such as sugar, for example, would have an I of 1, a Van Hoff factor of 1. You may not be able to make a 2.14 molal solution of sugar, but it would have a Van Hoff factor of 1. So number 31, it says, what is the order of the reaction with respect to the reactant whose concentration is graph versus time in the graph below? So we have here the reactant concentration versus time. So you are allowed a cheat sheet on the test, so I suggest you put the following on your cheat sheet. For a 0th order reaction, if we have concentration on the y-axis and time on the x-axis, we should see this. For a first order reaction, to get a linear regression, we need the ln of the concentration on the y-axis versus time on the x-axis. And if you remember the blue food coloring, this was what we got. And so it'll fit on the screen. I'm going to put this over here. For a second order reaction, we would want to have 1 over the concentration versus time, and this is the only one with a positive slope. So here the slope is k, here the slope is negative k, because this is a negatively sloped reaction. So in this case, we have concentration versus time. Concentration versus time is 0th order. So finally, I'd like to just conclude with a couple comments. First of all, I hope you have enjoyed the general chemistry lab courses, and I hope you learned something. I can see from the Friday projects that you certainly have, not to mention the lab reports themselves. The other thing I want to remind you of is you are allowed a cheat sheet, which can be one side of one piece of paper. I so strongly recommend you take advantage of that. As you go through this, you may find some good stuff to put on your cheat sheet, which can help you for the final exam. And finally, I just wanted to remind you that the midterm exam, the practice midterm exam, would be worth a review as well because the final exam is cumulative. So thanks for watching the videos this semester, and I hope you enjoyed the course.